library create. A library create is compiled into a library, and it doesn't contain a main function, but it's considered a collection of reusable code that can be shared across multiple projects. And the create root is the source file that is the root module of the create. In binaries, it would be source main.rs, and in libraries, it would be the file lib.rs. Then we have modules, and a module is a way of organizing code by grouping together related items. Modules can be imported using namespaces, avoiding naming collisions. It also controls the privacy of its items like functions, structs, enums, and so on. When compiling, the compiler starts from the create root. We have seen in a binary create this would be in main.rs, and in a library it would be lib.rs. Then it checks if the modules are declared and looks for submodules. Submodules could be directly written in line with curly braces. It could be written in a separate file which has the module name ending in .rs, or it could be in a separate directory which has the same name of the module and a mod.rs file inside it. And we'll do exercises and you will see how that works. So in case you want to follow these exercises, you actually have to install Rust on your system. So you can go to rustlang.org and then you can click install. And over here, it will give you a command you can copy. Then running a terminal. And you can just copy this into your terminal. Now I'm on a Unix-like operating system, meaning I will use the Linux command, but the website will recognize your operating system and provide the appropriate command. So if you're on Windows, it will give you a command that you can paste into PowerShell, for example. So proceed with installation default. You can then press 1 and enter. Now I have already downloaded that, so I won't run it again. And then to check if everything is installed correctly, you can use these commands. First of all, we check, is the Rust compiler installed? If you get back a version, it means everything is installed. Then we check for cargo. This is fine. And rustup. And rustup is used for updating the version of Rust on your local system. Alright, so let's now see the exercises. A package is a project which you create with cargo in most cases, so it contains a cargo.toml file in it. So create a package with below layout. Now I will do that directly in the home directory, but you can do it at any location you want. So to create a new package, we can use cargo new and then provide the name of the package. So we want the name here to be hello package. And as you can see, the package has been created. So let's see cd hello package, and we are now inside our created package, right? So we have here cargo toml and a source directory. Let's see source. And if I print out the contents in main, as you can see, it contains a simple program that prints out hello world. So let me actually do it like that. So over here, if I now do a tree command, as you can see, we have exactly the same file structure here. We have a cargo toml and then a source directory with main.rs inside. Let's print out the cargo toml. And as you can see, this matches the file in the exercise. Create a package with below layout. So over here, we want to create a library. So I'm back in my home directory and we can create the library crate right now. Let's do cargo new, then the package name here. And then we have to provide the lib flag, right? So this will then create a library. And then let's cd into that. And as you can see, we have cargo toml and a source directory. Now, let me print out the cargo toml file. And as you can see, again, this matches. And if we go to the source directory, as you can see over here, we have a lib.rs file. And this just has a basic add function over here together with some tests. All right. Fill in the blank with your answer. What's the difference between package number 1 and package number 2? Now the difference would be package number 1 is a binary crate. And package number 2 is a library crate. All right. Crate. A crate is a binary or library. The crate root is a source file that the Rust compiler starts from and makes up the root module of the crate. In package hello package, there is a binary crate with the same name as the package, hello package, and source main.rs is the crate root of this binary crate. Similar to hello package 1 also has a crate in it. However, this package doesn't contain a binary crate, but a library crate, and source lib.rs is the crate root. So what's the name of the library crate in package hello package 1? The answer would be, hello package 1, right? Because as we've seen over here, in the package hello package, there is a binary crate called hello package. And that means in a package hello package 1, the name of the library crate would be hello package 1. And by the way, a package is what we have seen over here. Basically, when we create a new project, right? When we create a new project, we create a new package. And a package consists of a cargo.toml file and a source directory together with other stuff. Add a library crate for hello package and describe its files tree below. Alright, so we want to add in the hello package a library crate. So let me remove this over here and we will go inside hello package. Now over here in the source directory, we want to create a new library crate. As you can see, we have until now a binary crate. So let's create lib.rs. Touch is a Linux command that allows to create a new file. So then we would have librs and main.rs. So when we look at the tree, as you can see, we then have the cargo toml, the source directory, and 2 crates, 1 library crate and 1 binary crate. So this would then hold lib.rs and main.rs. After this step, there should be 2 crates in package hello package, a binary crate and a library crate, both with the same name as the package. A package can contain at most 1 library crate, but it can contain as many binary crates as you would like by placing files in source bin directory. Each file will be a separate binary crate with the same name as the file. So create a package which contains 3 binary crates, hello package, main1, main2, 1 library crate. So what we want over here is to have in the source folder the lib.rs and main.rs. Then inside the source folder we want to have a bin directory which holds main1 and main2. Right? So as we've seen, we can have as many binary crates as we want in a package, but only 1 library crate. And over here we have some other directories. So we have tests for integrated tests, benches for benchmark, and examples. So let's create these over here. So as you can see, inside source we already have a library crate and a binary crate. Now we want to create a new directory called bin. Then we cd into bin and we create main1.rs and main2.rs. So again, when we go to the root of the package, as you can see, we have cargo toml, the source directory. We have inside the source directory a bin directory holding 2 binary crates, main1, main2, and we have in the source directory lib.rs and main.rs. Yep, as you can see, the above package structure is very standard and is widely used in many Rust projects. So let's see modules. Modules let us organize the code within a crate into groups for readability and ease of reuse. Module also controls the privacy of items, which is whether an item can be seen by outside code, public, or is just an internal implementation and not available for outside code, private. We have created a package named hello package in previous chapter and it looks like this. Now we actually created over here a bin directory, so let's delete that. I go into source and then remove the bin directory. So as you can see, the tree looks exactly the same. Now it's time to create some modules in the library crate and use them in the binary crate. Let's start. So as you can see, we can define some code in the library crate and then use it in the binary crate. So implement module front of house based on the module tree below. So in the library crate, we want to create a module front of house, and this should then hold 2 submodules, hosting and serving. Now hosting holds 2 functions and serving holds 4 functions. So as you can see, we would do that in the library crate. All right. And again, modules allow us to structure our code. So let's open lib.rs and I will copy this over here. So we have to implement front of house. Now we have seen that front of house module should contain two submodules, namely hosting and serving. Like that. So we have a front of house module that contains two submodules, hosting and serving. Now we want to add these functions over here, add to waitlist and seat at table in the hosting module. Add to waitlist, add to waitlist and seat at table. So as you can see, front of house containing one submodule hosting, holding two functions over here. Now let's see serving. I will just copy that. Like that. And doing it like that. As you can see, the serving module holds three functions. And when we run the code, actually, we can use the cargo run command. And as you can see, this is compiling, but it gives us warning that we didn't use these functions over here, which is okay. And of course, hello world will get printed from the binary crate, right? Because main just prints out hello world. Let's call add to waitlist from a function eat at restaurant, which is within the library crate root. So inside lib.rs, we are below the module front of house. We are creating a new function. Like that. Call add to waitlist with absolute path. So it's like in a file system, you can have absolute paths and you can have relative paths. So in this case, we want to use the absolute path to the add to waitlist function over here. So we would use for the absolute path the crate root. Then we want the front of house module. And we want the submodule hosting, right? And then over here, we can call the function like that, add to waitlist. Now this would be considered the absolute path. Now over here, we are using the relative path. So we are actually already in the crate root, right? So that means we don't need to use crate here. We can directly access front of house. Hosting. And then call the add to waitlist function. Now, as you can see, it gives me here an error module hosting is private. So we can make this public using the pub keyword. All right. Now the same thing with the functions. Let's make them public like that. You can use super to import items within the parent module. So again, in lib.rs, we want to create another module. So let's copy that. I will put it below the front of house. And as you can see over here, we have the back of house module with two functions declared inside it. So we have fix incorrect order, and inside this function we call the cook order function over here. Fill in the blank in 3 ways: using keyword super, using absolute path. So in order to access the function over here, serve order, let's first use the super keyword. So super means we go 1 level up, right? So we are here inside the module back of house. So we go 1 level up, which would be the create root, right? lib.rs. So we use super, and then we can access front of house, and I guess hosting, no, serving, and serve order. Like that. And again, serving is private. Let's do that. Let's make it a public function. And again, serving here is private. So let's make that public. And also the function here. Like that. And the second way would be using absolute path. So again, we can use here create, right? Create would refer to lib.rs because it is the create root of this package. Separating modules into different files. So as you can see, we want to put these modules into their own distinct files. Please separate the modules and codes above into files resident in below dir3. So as you can see, we have here main and librs crates, and here we have the modules we want to split up. So we have the module front of house, holding hosting and serving. These are submodules and mod.rs. And we have over here back of house.rs. Now we have said that there are 3 ways to declare modules, right? The first way would be in the create root, for example, lib.rs. We define a module and put it right inside the curly braces, right? All the code is inside these curly braces, right? The second way would be to, in lib.rs, declaring the back of house module, but without curly braces, right? Only declaring like this, for example. Only declaring the module. And that means the compiler will then check, is there in source directory a file named as the same name as we gave it to the module, right? So we declared a module in lib.rs, and then we have to create a file ending in .rs with the same name as the module we have declared. And the third way would be, if we want the module to be a subdirectory of source, then we have to again declare front of house inside lib.rs the same way we did before, but we create a directory instead of a file with the same name as the module. And then, very important, the code of the module will then be in mod.rs. Now in our case, we are declaring in mod.rs two submodules, hosting and serving. All right. So we want to have this code separated in different files, and this is how it should look like. So let's start with back of house. All right. I will copy that. And first of all, I will delete anything in here. And let's declare the module back of house, right? Now we have here declared a module. As you can see, the file is not found. So we can here declare back of house .rs, and then we can put the code of the back of house module directly into this back of house file. Removing this over here because we have already declared the module. And as you can see, back of house file now contains only the code related to this module. Again, we have in lib.rs declared the back of house module. Then we have over here created a file that has the same name as the module, right? And in here we are providing the code like that. And because we have already declared the back of house module, we don't have to redeclare it inside here, right? Now, as you can see, we also want front of house. Now the difference is front of house should be a directory holding two submodules. So let's first of all, in lib, we want to declare front of house module like that. Then we create the directory with the same name as the module. Like that. Then the first thing is we create a file mod.rs. This is now the create root of this. This will be considered the root of this module, mod.rs. And as you can see, we want here inside front of house two submodules, hosting and serving. Let's declare them. Like that. And then we can create both of these files. Let's start with hosting. And we just take all the code from the hosting module here. Like that. And let's create serving. And we just take the code here from this serving module. Like that. Let me remove the comment. So, and now if we go back to the source directory, As you can see, we have back of house. This is a module. We have front of house, hosting, and serving. These are two submodules. And we have here mod.rs, exactly like we wanted here. Now over here, by the way, this function eat at restaurant will be directly in the lib.rs. So as you can see, instead of defining the module and putting all the code in curly braces, meaning inline, we can use different files to restructure and reorganize our code. And this makes the lib.rs file much more clean and readable. Accessing code in library crate from binary crate. Please ensure you have completed the fourth exercise before making further progress. You should have below structures and the corresponding codes in them when reaching here. So we have done that. Now we will call a few library functions. Now we will call a few library functions from the binary crate. So let's copy that into the binary crate. Like that. Now we want to call a function. So the output should be sit down please, and then a second function which returns yummy yummy. Now, as you can see over here, we have to call the eat at restaurant function to get back yummy yummy, and sit down please would be in the front of house module, in hosting, and seat at table function. So let's see. First of all, I want here the module front of house. Alright, because the binary crate and the library crate are separate from each other. So the binary crate over here can't know what is defined in the library crate. And then over here, we can, as the crate module, and then here we can use an absolute path providing the crate root. Now we have to actually provide here the name of the crate, meaning hello package. All right. And then we can call front of house. And let's see, front of house, hosting, seat at table. Seat at table, like that. And then over here we call hello package, and then eat at restaurant. This is defined in our lib.rs. So again, instead of writing here crate, we write the name of the package because we are here in the binary crate. So we can use the crate keyword in lib.rs, but in main.rs we have to provide the name of the package. Let's run that. And as you can see, we have some errors. Module serving is private and module hosting is private. So to actually access that from the binary crate, we have to make them public. So let's see. First of all, we go to lib.rs and we want these two modules to be public. So let's make them pub like this. which means that these two modules are now accessible for our binary crates, the main.rs file. Then let's go to front of house. And let's here make these two modules or these two submodules also public. Like that. And if the module itself is public, that doesn't mean that the inner functions, for example, or structs or anything that is inside the module is also public. So we have to declare here, as you can see, this is already done, that these functions are also public if we want to access it. And as you can see, serving also has the public functions. Now let's check again in lib.rs because we are calling here a function. All right, this is also public. Let's run it again. And as you can see, this is actually compiling. It just over here complains that we didn't use some of the functions, which is okay at the moment. Now, instead of just asserting, let's actually print that out. Yeah, let's do it like that. As you can see, the output will be sit down, please. Let's call the second one. So we want to get this. Like that. Let's see. All right. I copied here the whole assert. We don't need this actually. Let's see. And as you can see, the output will be sit down please and yummy yummy. So we have successfully restructured and reorganized our whole code into different files and folders, meaning it is much more organized and much more readable. All right, see you in the next topic. We will now take a look at the debug and display traits. So types which want to be printable must implement either debug or the display traits. And automatic implementations are only provided for types in the standard library. So this doesn't apply to our customly created types. A debug trait can be implemented by simply using the derivable trait. And a display trait must be manually implemented. Let's see. We have here println and format. Printing is handled by a series of macros defined in standard format, some of which include format, write formatted text to string, print, same as format, but the text is printed to the console. Println is the same as print, but a new line is appended. ePrint is the same as format, but the text is printed to the standard error. And ePrintln, same as ePrint, but a new line is appended. All parse text in the same fashion. all parse text in the same fashion as a plus Rust checks format correctness at compile time. So let's see, we have here a string literal, and we use here the format macro, meaning the return type will be string. And we want here s to hold a string of hello world. So again, we use the format macro like we would use the print ln macro we have been using. So in this case, we want to take s1 over here and then just append the rest. So we take hello, this will be placed here, and then the rest. And this is compiling. Let's actually print that out. As you can see, this would be the output when printing out s. Print ln, fill in the blanks to make it print hello world, I am, and then on the new line, sun face. So over here, we want to use print, because as you can see, I am should be on the same line. So as we've seen, print macro doesn't append a new line character. Now a new line is defined in C like that, all right? And this is a symbol that the compiler knows that it should treat it as a new line. But in this case, print doesn't append it, so the next line will be on the same line as this print statement. So let's use here print ln, because as you can see, after I am, we want to have a new line. And then over here, we can again use print ln. And this would be the output. Debug and display. So all types which want to be printable must implement the standard format formatting trait, debug or display. Automatic implementations are only provided for types such as in the standard library. All others have to be manually implemented. Let's first look at debug. The implementation of debug is very straightforward. All types can derive the debug implementation. This is not true for display, which must be manually implemented. And we have used that before. This is the debug notation, must be used to print out the type which has implemented the debug trait. So as you can see over here, we have a custom type. This structure cannot be printed either with display or debug. To make this struct printable with debug, we can derive the automatic implementations provided by Rust. So again, we can use a derivable trait, meaning this struct over here implements the debug trait, meaning we can print it out using debug notation. So fill in the blanks and fix the errors. As you can see, we have here a custom type structure holding an i32 value. Types in standard and Rust have implemented the debug trait. So as you can see, this is of type i32. Now all of the types in the standard library have implemented debug or even display. So we can use here the display notation, and this will print out fine. Now over here, we must use debug notation because this is a type that we have created. And again, to use the debug notation, we have to derive the debug trait. Like that. And that means structure implements the debug trait, and we can then print it out. So this I32 type will be printed automatically because it's a type defined in the standard library. And over here, we just had to derive the debug trait and then use debug notation here. So format debug definitely makes one type printable but sacrifices some elegance. Maybe we can get more elegant by replacing this notation with something else, but not this. Alright, let's see. We have here a custom type that derives the debug trait. Then we are here instantiating it. And when we now execute the program, as you can see, the output will be like this. Now we want the output to look something like that. And we can for that use the pretty notation, just adding this hashtag symbol between the colon and the question mark. And then the output should look much more pretty. As you can see, the output will then be like this. And notice we first had to derive the debug trait in order to print it out using debug notation. We can also manually implement debug trait for our types. So as you can see, we have here two custom types, structure and deep. Now structure holds a type of I32 and deep holds a type of structure, meaning these are basically nested. So we have deep, which holds a structure, which holds an I32, right? The problem with derive is there is no control over how the results look. What if I want this to just show a 7? So as you can see, we are here instantiating it with a value of 7. Now when we print it like that, then as you can see, the whole structure will get printed out, but we only want the value over here. So what we can do is we implement the debug trait manually, meaning we can manipulate the output. So let's see the debug trait in the documentation. And as you can see, this is the debug trait as defined in the standard library. So let's copy this function signature. So we can then over here implement the debug trait. And this is found in a module and this is inside the module FMT from the standard library. And we want to implement it for the deep over here. Now we remove that and we also remove that because we are implementing debug trait manually, right? We don't need the derived implementation. So let's see, deep. Then I will copy the function signature. So here we can use a custom type FMT result. And you know what? We can use a namespace here. So then we don't have to write here standard all the time. Like that. I can delete this lifetime. And now we can implement the debug trait, namely this FMT method. So again, we want to write to a buffer. So we use the write macro. And it should write to this formatter, which is provided by the debug trait. And then over here, all we want to actually print out is, in this case, self, right? The instance over here. And then we access the first element. So when we access the first element in a tuple, we use the dot notation like that. And inside here, we have now accessed structure and we want to access this value, the structure struct holds, right? So we again use 0. And that's basically it. Now it should print out. And of course, over here, FMT formatter. This is also from the FMT module. And as you can see, now 7 will print. So all we did over here is manipulating how the output of the debug trait looks like when we use debug notation. And as you can see, we have defined for the deep custom type over here how the output should look like. So the output will just be the inner element of deep and structure, right? This I32. And we just access that and write it to this buffer. All right. Display. Yeah, debug is simple and easy to use, but sometimes we want to customize the output appearance of our type. This is where display really shines. Unlike debug, there is no way to derive the implementation of the display trait. We have to manually implement it. Another thing to note, the placeholder for display is this and not that. So this would be for debug trait. For display, we are using that, and you know that already. So make it work. As you can see, again, we are using the FMT module, and we have a custom type, point2D, holding two fields of type F64. Now we want to implement the display and the debug trait for this custom type. Meaning, when we instantiate this point2D, then we can pass the instance over here and it will give us this output, right? So we are using here the display notation and debug notation. And as you can see, we can here define different outputs. So when we pass an instance of point, then the display trait actually will output something like that. If we use debug notation, then we want the output to look something like that. And that's what I mean when I say we can manipulate how the output of a custom type will look like. So I will take over here this method and I will just copy it over here. Now let's first implement the display trait. As you can see, we want the output to look something like that. So we define here display, the X field, the value of X field, and then plus the value of the Y field, and we have here an I, okay? Like that. And we can access these fields using normal notation self.x and self.y, right? And for debug notation, we want the output to look something like that. So let's copy this, put it inside here. And as you can see, we want here the value of the X field and here the value of the Y field. And as you can see, we are here using curly braces, and this is usually for the placeholder. So what we have to do here is using two of them, meaning this curly braces over here will basically be escaped. All right. And then over here, we have to provide the arguments self.x and self.y. Let's see. And this is compiling. Now let's see the actual output. As you can see, I'm using display notation and debug notation and just provided an instance of the point to the type. And as you can see, this will then be the output. So question mark operator implementing FMT display for a structure whose elements must be handled separately is tricky. The problem is each write generates a FMT result which must be handled in the same place. Fortunately, Rust provides the question mark operator to help us eliminate some unnecessary codes for dealing with FMT result. So let's see. Again, we are using the FMT module and we have here a custom type, a struct list, a tuple struct list holding a vector of I32 elements, right? Over here we are instantiating this list with a vector holding 1, 2, 3. Now as you can see, when we put this list over here into the format macro, then we want the output to look something like that. So we want to print these square brackets, the index, colon, and then the actual value. Now let's see how this would be implemented. Notice over here we are implementing the display trait, so we can then use it to display the type directly. So as you can see, this is the function signature from the FMT module. And as you can see over here, we return a type of FMT result. Now this is a type. Now this would be a type alias, and we have covered that. Now over here, we want to extract the value using tuple indexing and creating a reference to vec. So the first thing we do is we want to access the vector in the list struct, and we do that using tuple indexing, right? We want the first element because there is actually only one element on here. So we access that, meaning we will get back a reference to a vector holding I32 types, right? Here we are taking a reference. Now, then we have basically unwrapped this vector into this variable. Now, as you can see, we use the write macro to write to this buffer this square bracket, because as you can see, this is what we want to output. So the first thing added to the buffer will be this square bracket. Then iterate over v in vec while enumerating the iteration count in count. So we take this vector and we iterate over it and enumerate, meaning we will get back a tuple holding the index and the actual value. Then for every element except the first, add a comma. Use the question mark operator to return on errors. So as you can see, if count is not equal to 0, meaning if it is in fact the first element, then we don't add this comma, all right? Because we don't want to look something like that. So this is only after the second iteration that this comma will be added. And then we write the actual value over here. And this iterates 3 times, right, for each element. And then in the end, it will put into the buffer this square bracket. So when we run that, as you can see, the output would be something like that. But this is the output that we want. So what's missing over here is we didn't include the indexes, right? So what we can do over here, we want here to be the index and then a colon like here and a space and then the value. So we have the index in this count variable. So let's use that. And again, we can then run the program and this succeeded. So let's actually print that out. As you can see, this would be the output. So we can really manipulate the output of our custom types using the debug and the display traits. And by the way, as you can see, we are here using the question mark operator because this over here could potentially fail, right? That's why we are using this here, and we use here the result type from the FMT module, just in case any of these operations here fail. Alright, see you in the next topic. So let's take a look at lifetimes. Now lifetimes are only necessary when dealing with references, and even then, most of the time the compiler can actually infer the lifetimes and we don't have to worry about it. So let's see. A lifetime is another kind of generic, ensuring that references are valid as long as needed. Every reference has a lifetime, which is the scope for which the reference is valid. Most of the time this is implicit and inferred, so we don't have to worry about it. Sometimes though, lifetime annotations are needed, and that's the case if the compiler can't infer it. And lifetime annotations is a concept which most other programming languages don't have. So even for experienced programmers, this sometimes looks a little bit confusing, but in actuality, it's a very simple concept and you will understand it very quickly. So actually, the main aim of lifetimes is to prevent dangling references, also called dangling pointers. So let's see, we are here in main and we declare a variable r. We don't initialize it with a value, but just declaring it. Meaning the compiler will actually infer a lifetime of a for this variable. And the lifetime a in this case is valid until the end of the main scope, right? Then over here we have an inner scope. And in this scope we are initializing variable x with a value of 5. So the compiler will annotate this variable to be of lifetime b. And as you can see, lifetime b is only valid until the end of this scope. Now then we are assigning a reference to x to the variable r, meaning the variable r we have declared here holds a reference to the variable x. The problem here is that when x goes out of scope at this point, then r points to something that is not valid anymore, right? And that's the aim of references, to avoid exactly this scenario. Now, to understand lifetimes, you have to understand the borrow checker in Rust. So the borrow checker compares scopes to determine whether all borrows are valid. It's a key part of Rust's ownership system. It tracks lifetimes of references and ensures that they don't violate the ownership rules. These rules ensure that a value is not accessed after it has been moved or freed from memory. And important, a reference to a value must never outlive the value itself. So you have to remember especially the last line. A reference to a value must never outlive the value itself. So when we go back here, as you can see, we have here a reference to value 5. Now the problem is that this reference outlives the value itself, meaning x holding this value we are referencing to goes out of scope, meaning the reference on here lives longer than the actual value it is referring to. Alright? Let's see. The compiler uses lifetime to ensure all borrows are valid. Typically, a variable's lifetime begins when it is created and ends when it is destroyed. So, the scope of lifetime. Annotate the lifetime of I and borrow 2. Lifetimes are annotated below with lines denoting the creation and destruction of each variable. I has the longest lifetime because its scope entirely encloses both borrow 1 and borrow 2. The duration of borrow 1 compared to borrow 2 is irrelevant since they are disjoint. So when we look at this program here, what you see is that we have here initialized variable I, right? Now this variable I over here lives until the main scope ends. All right? Basically, it outlives this scope and this scope. Now over here, we are assigning a reference to I to borrow 1, right? So borrow 1 lifetime starts. And then we are just printing out borrow 1. Now over here, borrow 1 will go out of scope. But it doesn't matter because the value itself still lives on. Alright? And over here the same thing. We have borrow 2 which holds a reference to I. Meaning that borrow 2 lives inside the scope. So we print here borrow 2 and then it will here go out of scope. But again, the value here lives on. So the actual value outlives the borrows or the references. Alright? Example 2. So over here we have a variable x with a value of 5. And then over here we have a reference to x assigned to variable r. And then we are printing out r. Right? So if we execute that, it will compile. Because again, as you can see, we are declaring here the variable x in this scope. So variable x will live until the scope ends. And the same thing for the reference to x. So the reference to x is assigned to r, meaning r will live until the end of this scope. So the value and the borrow to the value are both valid. Alright? And over here you can see the lifetime annotations. The important thing here is that both the value itself and the reference to the value are valid, right? The reference here doesn't outlive the actual value it is pointing to. Annotate R and X as above and explain why this code fails to compile in the lifetime aspect. And that's actually the example we have seen. So we are here declaring R, and over here in this inner scope, we declare a variable X and initializing it with a value of 5. And then we are assigning a reference to X to R. The problem here is X will go out of scope, so R still points to this location, but this over here has gone out of scope, right? So Rust won't allow you to compile this program, and you will get a compiler error saying X does not live long enough, right? Because the reference to the value lives longer than the actual value lives, right? Meaning the lifetime of X is shorter than the lifetime of R. or the lifetime of X holding the value is shorter than the lifetime of R holding the reference to a value, and this should never happen. So lifetime annotating, the borrowed checker uses explicit lifetime annotations to determine how long a reference should be valid. But for us users, in most cases, there is no need to annotate the lifetime, because there are several elision rules. Before learning these rules, we need to know how to annotate lifetime manually. So, ignoring elision rules, and that's the next topic, lifetimes in function signatures have a few constraints. Any reference must have an annotated lifetime. Any reference being returned must have the same lifetime as one of the inputs or be static. So over here we have a function print1, and it takes as an argument a reference to an i32 type. Alright? Now this is how we would annotate a lifetime. It's actually very similar to generics, but we use this apostrophe syntax and a lowercase letter, by convention just going from A, B, C, D, and so on. So in this case, we annotate here that the reference here is of lifetime A. So when we have over here a lifetime annotation, then we can provide here, then we can annotate it here for our reference, right? And again, we are just dealing with lifetimes when we are dealing with references. So in this case, we say the reference to the i32 type should be of lifetime A. Now, when we annotate that to our function, it means that the lifetime A must at least live as long as the function itself. Or we could also say lifetime A must outlive this function. So the past reference over here must outlive this function. And this is just ensuring that the reference passed here lives longer than this function, meaning we can ensure that this function always deals with a valid reference, right? And all we do here is printing out X. Mutable references are possible with lifetimes as well. So if you would have a mutable reference, you would annotate it like that. First, after the ampersand, of course, you will always put the lifetime annotation and then the mute keyword, and then of course the type. Multiple elements with different lifetimes. In this case, it would be fine for both to have the same lifetime A, but in more complex cases, different lifetimes may be required. So as you can see, we can define more than one lifetime. Over here we have lifetime A and lifetime B, meaning the references passed to this function could be of different lifetime. But again, lifetime A and lifetime B must outlive this function. So the past references over here must outlive the function, right? And returning references that have been passed in is acceptable. However, the correct lifetime must be returned. So let's take a look at the function passX. As you can see, it takes two arguments and both of them are references. Now, this would be of lifetime A and this would be of lifetime B. Again, both of these references must outlive this function. And we are just returning X, which is annotated with a lifetime A, meaning the return type will be a reference to an i32 with a lifetime of A, right? This would be the type that is annotated to the X argument here. if we would here have y and we return y, then we would do it like that, right? Because we are returning a reference with a lifetime annotation of b. So as you can see, we have here two variables holding i32 types. And then we are passing to all of the above functions the reference to these two variables, right? Because all of these functions over here expect a reference to an i32 type. Now, in this case, this program will compile. As you can see, this is compiling because we have here declared x and y in the main scope, meaning they are valid until the end of the scope over here, right? So the x and y references we pass to the functions outlive all the functions, which is a requirement, right? The passed references must outlive the function, so we don't have to deal with dangling references. And so let's see an exercise to understand it even more. Make it work by adding proper lifetime annotation. So over here we have the function longest that takes two arguments of type string slice. Now we then test the length of these string slices, and if x is longer than y, then we return x. Otherwise, we return y. So if we go over here in the main function and let's do some variables. As you can see, we have two string literals, long and longer. Now, we would pass that to this function over here. Now, it could be possible, in this case, the return type is known at compile time, but sometimes this is decided at runtime. And when we are passing these arguments to the function over here, let's do that actually. And notice we don't have to pass here a reference because string literals are already references. All right. Now, if we would compile that, this would actually fail, right? Missing lifetime specifier. So what we want to achieve here is, first of all, we want to add a lifetime parameter like that. And then we want to define the lifetimes of these references. Now, in this case, the function over here could either return x or y, right? Depending on which argument has the longer string, right? So sometimes it might be x that is returned and sometimes it might be y. So we can't be sure if we annotate here a and b like that. We don't know which one will get returned. Is it A or B? It depends on the arguments, right? So what we can define here is that X and Y, these two arguments, have the same lifetime, meaning these two references share the same lifetime. They must be declared in the same scope. And both of them, of course, must outlive the function longest. So in this case, this is what we are providing, right? We are declaring x and y over here in the main scope. So when we call the longest function with these two references over here, it means that these two references still live on even after this function call, all right? Because again, the reference of x and y will live until the main scope ends. Now, because we have here defined that both of these references have the same lifetime, it is clear that the returned string slice must have the same lifetime, either x or y, right? Let's see. And as you can see, this is compiling. In this case, longest will return y because it is longer than the x string, all right? A must live longer than the function. Here, reference to string foo would create a string followed by a reference. Then the data is dropped upon exiting the scope, leaving a reference to invalid data to be returned. Fix the error in 3 ways. As you can see, we have the function invalid output. We define here a lifetime parameter a and declare that the returned reference should be of this lifetime. Now, the problem here is we are creating a new string and returning a reference to it, right? We are returning a reference to a string. The problem is this string was declared inside the function. Now, when the function returns to the caller, it means the string over here will get out of scope, right? Because it is declared inside the function. So again, if we call, for example, if we call this function, then we would get back a reference to a string, right? The problem is that the reference points to something that isn't valid anymore. This string declared here got out of scope. So x points to something that is not valid anymore. So returning a reference to something declared inside a function is a really bad idea. Now what we can do over here to fix that, and this is probably the easiest fix, we just return the string itself, right? So then ownership will be transferred and x will be the owner. All right, let's print out x. As you can see, this is working because we are here declaring a string and then return it, meaning the ownership of the string will then be returned over here, right? So x will become the owner of the returned string from the invalid function. The second way to fix that would be returning a string literal, right? And a string literal actually has always a static lifetime. We will come back to that, but that actually means that this reference is of static lifetime, meaning it is valid throughout the entire program. All right, because remember, a string literal is hard-coded into the binary, so it lives as long as the program lives. So then over here we will get back a string slice, right? Let's see. And as you can see, this is also compiling. The third way would be we over here create a string. And then we can pass this string to the invalid output. So in this case, we want here to take a reference to a string right? We can also write it like that, because remember, a reference to a string will be automatically inferred to a string slice, right? So we are then passing a reference to this string, right? And what we want to return here is s, meaning we return here a string slice. And we can annotate a lifetime parameter and then we will print out x. Let's see. And this is also working, because as you can see, we have defined here a string, meaning s over here is the owner of the string. Then we are passing a reference of s to this function, right? We annotate here a lifetime a, meaning the reference over here passed to the argument s must outlive this function, which it does, right? We have declared s here, so even after this function call, s still lives on, right? And then all we do is we again return s, the past reference, right? So it will actually have the same lifetime as the past argument, right? Meaning we have here then a returned string slice. All right. Printfs takes two references to i32 which have different lifetimes a and b. These two lifetimes must live at least as long as the function printfs. So as you can see, we are here in the printfs function declaring two lifetime parameters, one for argument x and one for argument y. Again, we are dealing with references, meaning we care about the lifetimes. If these would be owned types, like so, then we don't deal with references, right? And then we just print out x and y, the provided arguments. Make it work. A function which takes no arguments but has a lifetime parameter a. So over here, we can see that we annotate a lifetime parameter a, and we have here an i32 integer. Now error, x does not live long enough. So we assign to y over here a reference to x. The problem again is that when we annotate this lifetime parameter, it says the lifetime a must outlive this function, which it doesn't, right? Because the reference over here, because the value we are referencing to is declared inside the function, meaning it will then be dropped at the end of the scope. Attempting to use the lifetime a as an explicit type annotation inside the function will fail because the lifetime of reference x is shorter than a. A short lifetime cannot be coerced into a longer one. So let's see, in main, we are here destructuring a tuple into the variables 4 and 9, right? So 4 will hold 4 and 9 will hold 9. Borrows of both variables are passed into the function. So we are then calling the printfs function with references to 4 and 9, right? This function over here. Any input which is borrowed must outlive the borrower. In other words, the lifetime of 4 and 9 must be longer than that of printfs. So again, when we annotate these lifetimes on a function, both of the lifetimes must outlive the function, or both of the references passed here must outlive the lifetime of this function, which they do, right? So 4 and 9 are declared in main scope, meaning they outlive this function over here. So this should actually work. So failed borrow contains no references to force a to be longer than the lifetime of the function, but a is longer. Because the lifetime is never constrained, it defaults to static. So as you can see, we have here declared the lifetime a, which states that the reference holding the lifetime of a must outlive the function. This is not the case, right? Because we are declaring the value inside the function itself. Now, when we remove that, actually, this over here will then work. All right, let's see. Let's see, structs make it work by adding proper lifetime annotation, a type borrowed which houses a reference to an I32. The reference to I32 must outlive borrowed. So as you can see, we have here a custom type, a tuple struct holding a reference to I32. Now in this case, we have to annotate the lifetime, and we do it like that. And then we pass it to the reference, like so, and that means this reference here must outlive this struct, or the instance we create from it, right? Similarly, both references here must outlive this structure. Again, we are here annotating the lifetime, and we say that both of them should have the same lifetime, which makes it easier, right? An enum, which is either an I32 or a reference to 1. So as you can see, again, we can annotate a lifetime basically like a generic type parameter. And over here, as you can see, this variant holds a type of I32. So the enum will be the owner of this type. We don't care about any lifetime annotation. We only care about lifetime annotations when dealing with a reference. Like that. Now let's see, we have here I32 and I32. And then we are instantiating the borrowed struct with a reference x, right? So as you can see, this would be the borrowed struct, and it holds a reference to x, which is I32, right? Now, as you can see, we define here that reference of lifetime a must outlive this struct or the instance of the struct, right? So x over here must outlive this instance, which it does, right? Because it is declared in main scope, meaning x and y will live until this point here. So they outlive the borrowed struct. And over here, as you can see, we pass here references to the x and y field of the named borrowed struct. So this would then be an instance. Now again, x and y in this case, first of all, they are declared in the same scope, so they can have the same lifetime, right? They both live in the same scope, and both of these variables will end at the same time. So this will actually compile, right? Everything over here is safe. So as you can see, we instantiate here the either enum, and one time with the variant ref holding a reference to x. Now again, as you can see, we have here lifetime parameter a, which states it must outlive the instance of the enum, which it does, right? X is valid all the time. And the second variant doesn't hold a reference. We just pass it the variable. Now, because this implements copy, it's an I32, it means that even then y will still live on. So either won't take ownership. It will take ownership of the copied value. Let's see if this is actually compiling. And this is compiling. Make it work. So over here we have the struct no copy type, and over here we have struct example, and as you can see we annotate here the lifetimes A and B, meaning over here the A and B field could hold references that have different lifetimes, but they can also be the same. All right, now let's see in main. A tied to fn main stack frame. So as you can see, we have here an I32, and over here we have declared a variable which should be of type example, but we haven't initialized it with values. All right, we haven't instantiated the example struct. Now notice here we have another scope, lifetime B tied to new stack frame. So then we have here an instance of the no copy type struct. And as you can see, fix me. So then we are instantiating example with the fields over here, passing it concrete values. As you can see, we are passing it a reference to var A, this, and a reference to var B. So the problem over here is that var B will go out of scope at this point, right? Meaning the example struct we have instantiated over here will hold the B field, which points to something that is not valid anymore. As you can see, we are here printing out example. Now, if we would print it out in this scope, then this would actually compile. And of course, this must be U32 because it is a U32 field here. As you can see, this is compiling fine. Now, even though we are here in a new scope, right? We have declared var B here in the inner scope, but even then, both of these references are valid, right? Because we are here then using example in the same scope. And we have noted that here that the lifetime of A and B are different, right? So the lifetime of var A is actually longer than the lifetime of var B, right? Because var A lives until the end of the main function, while var B lives only until this point. But again, this is safe and this is compiling because the var B we have created here and passed a reference to the example struct is valid. If we leave this over here, then this wouldn't compile, right? Because var B gets out of scope, and we over here say that both A and B must outlive example. All right, so example is used here, but not all references are still valid, which would lead to a compile error. But what we can do also is just removing this scope here, meaning everything is now declared in main scope. So this would also compile, right? Because all the references to these variables are valid. Let's see here, we have again struct no copy type and the example struct we have seen before. And as you can see, denoting that the lifetimes of these references might differ, but they can be the same, it's no problem. So let's see here, fix function signature. We have here the fix me function, which takes as an argument a reference to an example instance. And it will then return the B field from the provided argument, from the example struct, right? It will return this field over here, meaning a reference to no copy type, because that is what B is holding. Now over here we are instantiating no copy type, and we are instantiating the example struct. So we pass for the field A here a reference to 1, and for B we pass a reference to no copy type, right? And then we pass a reference of this example instance over here to the fix me function. Now let's first annotate the lifetime parameter. Again, we do A, and over here we say that the past reference to the example instance must outlive this function, right? Which it actually does, because here we are instantiating the example struct and passing it to a reference, and passing it as a reference to this function, meaning example over here will live longer than the function, right? And we can then define that no copy type must also outlive this fix me function, all right? Which it does, because again it's declared in main, meaning the end of scope will be at this point. So both the instance of example and the no copy type both outlive this fix me function. And as you can see, we can pass the same lifetime parameter because they are declared in the same scope, meaning they have the same lifetime. Methods are annotated similarly to functions. So we have here the struct owner holding an i32 type. So annotate lifetimes as in a standalone function. As you can see, we have here the implementation block for owner, and we implement some methods for this custom type. And this is how we would annotate lifetime parameters. Again, same thing. Again, same thing like in functions. Make it work by adding proper lifetime annotations. We have a struct important excerpt and a port field holding a string slice. Now again, string slice is a reference, meaning we have here to annotate the lifetime parameter. So that means the reference that the port field of this struct is holding outlives the entire struct, right? And over here we have a method implemented for the important excerpt struct. So as you can see, we are using a lifetime parameter here, but we have to actually first declare it like that. And that's basically it. It should compile. So when the struct over here declares a lifetime parameter, we have to declare it in the implementation block again. But we are here not using it, meaning we can do it like that, right? We don't care about this lifetime parameter here. And this lifetime parameter is declared only on the on the method, right? This is compiling, but there is an easier way actually. We don't have to use any lifetime here, right? Because we can define here that the string slice is static, meaning it will live throughout the entire program. All right. Elision. Some lifetime patterns are so common that the borrow checker will allow you to omit them to save typing and to improve readability. This is known as elision. Elision exists in Rust only because these patterns are common. For a more comprehensive understanding of elision, please see lifetime elision in the official book. So, I've prepared some slides. Let's see, there are 3 rules of lifetime elision. The first rule states compiler assigns a lifetime parameter to each parameter that's a reference. Second, if there is exactly one input lifetime parameter, that lifetime is assigned to all output lifetime parameters. Third rule, if there are multiple lifetime parameters but one of them is a reference to self or a mutable reference to self, the lifetime of self is assigned to all output lifetime parameters. So let's see an example. And before we see the example, as you can see, lifetime elision makes writing Rust much more easy. Until this point, we didn't worry and care about lifetimes, and that's most of the time the compiler just inferred it, so we didn't have to worry. Now let's see. Here we have the function first word taking a reference, okay, and returning a reference. So the compiler applies the first rule. Each parameter gets its own lifetime. So the compiler behind the scenes will annotate here a lifetime for this function and will annotate it for all the references, right? So the second rule applies because there is exactly one input lifetime. Again, we have only one argument that is a reference. So this gets assigned to the output lifetime, meaning the output reference here must then be the same reference, right? We are taking a reference, so it must be the same when we are returning a reference. So in this case, the compiler could infer the lifetime and we don't have to specify them manually. So what the compiler will do, he will just annotate the same lifetime as for the input argument, right? So this is all inferred. You can write it like that and it will compile. You don't have to worry about lifetimes. So let's see this example. We have the function longest that takes 2 references as arguments, okay? And it returns 1 reference. First rule, each parameter gets its own lifetime. So the compiler will come and annotate A and B. Each reference gets its own lifetime, all right? So here the second rule doesn't apply because there is more than one input lifetime. Also, the third rule doesn't apply because this function is not a method. We have now to manually annotate the lifetime parameters. So as you can see over here, the compiler cannot infer the returned reference here. Is it of lifetime A or is it of lifetime B, right? So it depends. If you return X, then you would annotate a lifetime of A. If you return B, then you would annotate a lifetime of B. And again, both lifetimes A and B must outlive this function. Let's see an example in a method. So as you can see, we have a method taking a reference to self, meaning taking the instance as a reference and doesn't take ownership. So here the third rule applies, which states that if there is a reference to self, then all references will have the same lifetime as self, right? So we can have here any number of arguments. All of them will take the exact same lifetime as the lifetime of self, because this is inferred and it makes sense, right? Because all of the provided arguments to a method must actually outlive the structure or the enum instance, all right? So all of the arguments here take implicitly the same lifetime as self, all right? So let's see, remove all the lifetimes that can be elided. As you can see over here, we have only one input argument. And the second thing is we don't even return anything. So we don't even have to care about the lifetime, because we don't worry that it might go out of scope, right? But in this case, we only have one argument, meaning the compiler is able to infer that. Over here, again, we have only one argument. But as you can see, the difference is we are returning a reference, right? So because there is only one argument here, the compiler can infer that the reference over here must be the reference that will be returned. So we don't have to annotate the lifetimes. So let's see, over here we have the longest function. And the first rule says that the compiler will annotate a lifetime for each reference, meaning it will create A and B because we have here two references, right? Two arguments. And it will annotate for the first argument A and for the second argument lifetime of B. Now over here, the compiler cannot infer which lifetime will get returned, meaning, as you can see, we are returning X. So the lifetime over here would be A, right? The lifetime of the argument X. But notice both of the references must outlive the function, right? Here we have a struct owner that holds an i32 type. Annotate lifetimes as in a standalone function. So as you can see, we have here methods implemented on the owner struct. Now again, when we have a mutable reference or an immutable reference to self, then we never have to worry about lifetime annotations, because this will get inferred by the compiler. All right, all references passed to these methods will get the same lifetime as self, or as the reference to self. Now over here we have to annotate the lifetime, because this is a struct and we want to ensure that the reference the name field is holding is actually living longer than the instance of a struct person, okay? And over here the same thing. Let's see if this is compiling. And this is compiling. What we could do also here, we could remove that and doing it like this. All right, this should actually also work. Okay, we have here to specify that the string is static. In this case, we have to explicitly state it. And as you can see, this is compiling. So you don't have to declare here a lifetime parameter. You can put here the static lifetime. And static lifetimes will be our next topic. Let's take a look at static lifetimes. So a static lifetime refers to a lifetime that lasts for the entire duration of the program's execution. Any reference or borrowed value with a static lifetime can be safely used throughout the program, and a static lifetime can be coerced to a shorter lifetime if needed. So we have seen string literals, and they are usually annotated using an ampersand and stir, but implicitly it would have a static lifetime. So string literals have a static lifetime because they are hard-coded into the executable, meaning they are valid throughout the entire duration of the program's execution. Let's see. Static is a reserved lifetime name. You might have encountered it several times. So a reference with a static lifetime is, for example, a string literal, and this would be the full type annotation. Static as part of a trait bound. So as you can see, we are here defining a generic type parameter, and we say that the argument provided should be of type T. Now in the var clause over here, we see that T must be of static lifetime, though they are all static but subtly different. As a reference lifetime, ampersand static indicates the data pointed to by the reference lives as long as the running program, but it can still be coerced to a shorter lifetime. There are several ways to make a variable with static lifetime. Two of them are stored in the read-only memory of the binary. Fill in the blank in two ways. So as you can see, we are calling here need static with an argument of v. So let's declare that here. And as you can see, the argument must be of type static string or string literal. All right. And then we are here checking, is the argument equal hello? So let's initialize it here. So the first way is just initializing it like that without any type annotation, because this is simply inferred by the compiler. So any string literal is hard-coded into the binary, means it lives as long as the program's execution, because the actual data of the string literal is living in the binary. The second way is just annotating the full type annotation, like that. And this static lifetime annotation here can also be omitted, so we can annotate it like this. As you can see, the compiler is able to infer the lifetime. Another way to make static lifetime is using box leak. Now this is an unsafe method, and I won't cover that because it's a more advanced topic. But I have solved it and will put it on my GitHub if you want to solve it for yourself. Static only indicates that the data can live forever, not the reference. The latter one will be constrained by its scope. So let's see, make a string literal and print it. So over here we have a string literal, meaning it's a string slice of static lifetime. Then we print it out. When static string goes out of scope, the reference can no longer be used, but the data remains in the binary. So at the end of this scope over here, this variable will go out of scope, meaning it's dropped. And that means we can't then use static string anymore because the variable has been dropped. Now, even though the variable has been dropped, the data over here is actually still living on, right? So this is living in the binary, A string literal is hard-coded into the binary, meaning it is of static lifetime, meaning it is valid throughout the entire program's lifetime. But of course, a variable is bound to its scope. So to make that work, we can take that and copy it over here, meaning the variable static string is valid until main ends, as you can see. Static can be coerced to a shorter lifetime. So over here, make a constant with static lifetime. So this over here is the static keyword, meaning we are here creating a constant. Now constants by conventions are always uppercase, right? And by the way, the difference between const this and this, now both of them live for the entire lifetime of the program. Both are of static lifetime. But the difference is that static will always remain at the same memory location, while a constant will get inlined. So when we use, for example, numConst here, then it will get inlined, meaning the compiler will basically copy that into the code in the function. So the memory location could change, but static always stays at the same memory location. So returns a reference to num where its static lifetime is coerced to that of the input argument. So as you can see over here, we have a function coerce static, and we have defined a lifetime parameter a. We define here that the input reference should be of this lifetime a, right? Meaning the reference we take as an argument to this function must outlive the function itself. Now we over here actually return this constant, right? Basically a reference to this constant. And we can, in this case, coerce the static lifetime of this num constant to a shorter lifetime. It's no problem, right? So a is shorter than static, right? A static lifetime is larger than this a lifetime here, meaning a reference with a static lifetime lives longer than a, because a only defines that it must outlive this function, right? But we can here coerce it to a shorter lifetime, so it matches with the lifetime annotated on the function. Make an integer to use for coerce static. So over here we make an integer, and then we pass a reference of this integer and call the coerce static function, meaning we here return a reference to an i32, right? Basically a reference to the number 18. And then we will just print out the result of this function call, right? Now, as you can see, we have coerced num here to a shorter lifetime, but this doesn't change the actual lifetime of the static constant, right? So even after this scope over here, we can still access num, because again, it's of static lifetime. It lives as long as the program is running. So even though we have here coerced it to a shorter lifetime, it doesn't matter. It remains static, right? Let's see, as a trait bound, it means the type does not contain any non-static references. For example, the receiver can hold on to the type for as long as they want, and it will never become invalid until they drop it. It's important to understand this means that any owned data always passes a static lifetime bound, but the reference to that owned data generally does not. So let's look at function printed. As you can see, we define here a generic type parameter, meaning the input argument here must be of type T. Now this over here is a trait bound, meaning we say the type T must implement the debug trait, and T cannot contain any reference that is not of static lifetimes. So all references T is containing must be of static lifetime, right? And over here we do basically the exact same thing, but using the impl keyword, right? This and this is actually quite the same. And then over here, as you can see, printed2 takes a reference to T, right? And again, T must implement the debug trait, and it cannot contain any non-static references, right? So I is owned and contains no references, thus it's static. As you can see, we are here initializing I with a value of 5, meaning I is the owner of 5. Now when we pass the owner to a function, then it would actually comply with this function signature, because owned types are also considered static. Okay? Now this would actually work, because again, I32 implements debug and it is considered static because we are passing an owned type, right? Oops, reference to I only has the lifetime defined by the scope of main, so it's not static, right? So a reference to I has a lifetime that is defined by this main scope, so it's not static anymore, right? So this would actually output an error, right? And this would be the same thing. Again, printed and printed1 would actually be very similar, right? Now this here actually works because we are here passing a reference to I again, right? So we pass a reference to I. And again, the reference to I would have a lifetime of this main function. Now the difference is here that in the argument we define that the argument should be a reference to T, meaning if we think away these ampersands, I would be T, right? So a reference to T would be a reference to I. Hope this makes sense. So that means, again, when we pass I directly, it would implement debug and it would be of static lifetime, right? So this over here would work. Now to fix these over here, we can do it two ways. We can create here the constant I. And again, constants have a static lifetime. As you can see, this is compiling. And the second thing is we can use the static keyword, meaning I is static. So this would pass because the argument we are passing or the references we are passing are all of static lifetime and they implement the debug trait, right? I32 implements debug and we have ensured that all of them are of static lifetime. Now the last one here again deals with box leak. I won't cover this, but again, The solution is in my GitHub. If you want to solve it, you can do that and then compare with my solutions. Alright, see you in the next one. So let's see closures. A closure is an anonymous function that is able to capture the values from the scope in which it is defined. And if you're coming from Python, then you might know lambda functions, and in JavaScript they are called arrow functions. And they can be defined inline, for example, as a function parameter. They don't require type annotations, and they can take ownership of a value by using the move keyword. So all functions and closures implement the fn traits, and that is the trait that defines the signature for closures and functions. It describes the types, the number of arguments, and the return type. There are three different traits. fn once, the closure can be called only once because it takes ownership of the captured values. fn mute, it might mutate a captured value. It can be called more than once. And fn, it doesn't take any ownership of captured values, it doesn't mutate anything, and it might not even capture anything from its environment. So let's take a look over here. We have here initialized the variable x with a value of 1. Now over here we would have a closure, and closures are defined like that. First of all, we have these symbols over here, and between them we define the name of the argument. And as you can see over here, we just add the argument with the value of x. So as you can see, the closure here is able to capture the value of x, something a function can't do, right? And we then assign this closure to a variable, meaning we then can call this closure and calling it like a normal function. So in this case, as you can see, we call the closure using the variable name closure and then providing it an argument, right? So actually this closure call should evaluate to 3 because we provide 2 here, meaning val will be 2 and adding x to it 1, so 2 plus 1 will be 3. So this closure captures the value of x and modifies it. The compiler will capture variables in the least restrictive manner possible. In this case, a mutable reference of x is taken rather than taking ownership because it's less restrictive. Let's see. Closures can capture the enclosing environments. For example, we can capture the x variable. That's the example we have seen. From the syntax, we can see that closures are very convenient for on-the-fly usage. Unlike functions, both the input and return types of a closure can be inferred by the compiler. So we have here a normal function. As you can see, it takes an argument of type i32 and it will just add 1 to the provided argument and returns it, meaning the return type will be i32. Now closures are anonymous. Here we are binding them to references. These nameless functions are assigned to appropriately named variables. So as you can see, we can here create a closure, and this over here are exactly the same. So type annotations in closures are not required. Okay. And then again, we assign the closure to a variable in order so we can call it. All right. Over here we have a variable I with a value of 1. And then we are just calling the function and these two closures with this value over here. And a closure taking no arguments, which returns an i32. the return type is inferred. So this would be a very primitive closure, just returning 1 when being called. So when we call 1 here, we would just get back 1. Let's execute that. As you can see, when we call this function and these two closures, it will just add 1 to the provided argument. And over here, we are just returning 1. Capturing. Closures can capture variables by borrowing or moving, but they prefer to capture by borrowing and only go lower when required. So they can capture the values either by reference, by mutable reference, or by value, meaning the closure will then own the type it captures. Okay? So let's see exercise 1, make it work with least amount of changes. So over here we are initializing a variable color with a string. So as you can see over here we have a closure and we assign it to print so we can then call it. Now this closure here doesn't expect any arguments, but it uses the move keyword, meaning the captured values will be moved inside this closure, right? So that means the closure here will become the owner of the captured value. This is not always the case. So for example, over here, a immutable reference is sufficient because we are just reading basically this data here. We don't mutate anything and we don't need ownership to print something out. But as you can see, printing 2 times over here will cause an error, right? So what we can do is we can remove the move keyword, and color can be borrowed immutably again because the closure only holds an immutable reference to color, right? That means when we don't move the captured value, we can then take a reference to color again. So this would hold a reference to a string. As you can see, we print here out 2 times color green because we are calling this closure 2 times. And this will take an immutable reference of this captured value. All right? And then we can take another reference of this string. So let's see exercise 2. Make it work. Don't use reborrow and count reborrowed. Don't modify assert EQ. So we have over here an I32. And by the way, this is mutable. And we have here a closure taking no arguments. Then as you can see, it captures this variable here. All right. And it mutates it, meaning count will then hold 1. And then we just print out count. Over here, we are calling this closure. And then we are taking a reference to count, meaning a reference to an I32, right? And then we are again calling this inc closure. The closure no longer needs to borrow mutable borrow count, therefore it is possible to reborrow without an error. So what is happening over here? We have seen that the compiler will take the least restrictive approach. So in this case, it will take so in this case, the count variable here will be captured as a mutable reference, right? And that would be a problem because as you can see, we are calling inc, and over here we call it again after here defining an immutable reference to count. So maybe you remember that you can either have one mutable reference or any number of immutable references, but not both at the same time. So this would be a problem. So we can call here the move keyword, meaning this closure here takes ownership of this value. Now again, because I32 implements the copy trait, it means it will actually get a copy of count. So count is still accessible even after this closure call, right? The closure will just take a copy of the value. And that means we can then take an immutable reference again to count and call the closure, right? And over here, the closure no longer needs to borrow a mutable reference to count. Therefore, it is possible to reborrow without an error. So as you can see, we are here taking a mutable reference to count again, because we don't use this immutable borrow over here again after this point, right? So this is allowed. Let's see. And as you can see, this is compiling, and here you can see that count has been modified. So let's see exercise 3, make it work in 2 ways. None of them is to remove take movable away from the code. So as you can see, we have here initialized a variable with a heap allocated I32 integer, right? Then over here we have a closure, and we capture here this movable variable. Now we have seen that actually the compiler will use the least restrictive approach. So in this case, because we have only a print line, it will take this variable here as immutable reference. We just need to print it out. Now over here we are calling the take function. As you can see, the take function takes an argument of any type, but it takes ownership, meaning when we call the take function with an argument, the argument will then lose its ownership. So take function will become the owner of movable in this case, right? And that means we can't call this closure 2 times, because in this case, again, the compiler will try to use the least restrictive approach, but in this case it's necessary that this closure over here will implement fn once, so it only can be called 1 time. Because again, over here, movable, when we call this take function, it will take movable and take ownership of it, because it's necessary for the compiler to do that to comply with this function signature. But what we can do is we say we want a reference, right? So again, the compiler will then implement the fn trait for this closure, meaning it can be called 2 times. Now we will see a lot of more example of these fn traits, so don't worry. It just means now, because we just need over here immutable references, the compiler will actually capture this variable here as an immutable reference, right? So nothing gets moved inside this closure, and movable will remain the owner of the data. For comparison, the following code has no error. So as you can see, we have again a heap allocated integer, and we have here a closure. Now, as you can see, we use the move keyword here, and in this case, this closure will capture the movable variable only as an immutable reference, because we here only print out the variable. We don't need a immutable reference, and we don't need to take ownership. So we can call this closure 2 times without any problem. Type inferred. The following 4 closures has no difference in input and return types. So this is actually a function, not a closure. But as you can see, all of them are exactly the same. So we can skip the type annotations, and we can even skip the curly braces if it is declared on the same line. So this over here is exactly the same as writing it like that. So over here we have an example closure taking one argument and just returning that argument. So then we over here call the example closure with a string, meaning over here this would be the argument provided and it returns a string. Now when you define a closure and call it with a concrete value, the compiler will then infer the types of the arguments and the return type. So in this case, the compiler will annotate the types like that. Right? We take an argument of type string and return the string. And that means that we then can't call the closure again with another type. This would cause an error, okay? What we have to do is to convert that to a string. Let's do it like that. So we get back a string here. And this is compiling. So let's see fn, fn mute, fn once. When taking a closure as an input parameter, the closure's complete type must be annotated using one of the following traits. Fn, the closure, uses the captured value by reference. Fn mute, the closure, uses the captured value by mutable reference. Fn once, the closure, uses the captured value by value, basically taking ownership. Alright, so make it work by changing the trait bound in two ways. So when a function accepts a closure as an argument, we have to actually define what will be the type of the arguments to the closure and the return type of the closure. Alright, and we over here can see that a closure implements one of these three traits. All right. Now over here in the fn1's function, we define that the func argument must be of type f. And here we define the trait bound. So f must be a type that implements fn once, taking as argument usize and returning a Boolean value. All right. And inside this function over here, we are just calling the provided func closure and providing it arguments. So as you can see, we have here a vector, and we call the fn1's function with an argument of a closure. As you can see, we can pass a closure as a function argument. Now in this case, this closure will implement the fn1's trait, right? Basically meaning it will take ownership of the captured values, and it can be only called once. So it takes as argument a type of usize, right? So, and this is necessary here because we are comparing the provided argument 3 and 4 with the return value of the len method, right? This len method is defined on vectors, and it will return usize. So z over here has to be of usize. We have to define that. And all this does is we can provide this closure an argument, and it will check is, for example 3 over here, is it the same as the length of this vector? Now the problem here is that we have to change the trait bound, because at the moment we are calling the func closure passed as argument to this function 2 times, while it implements fn once, meaning it can only be called once. Now what we can do over here is we take fn, right? Basically just taking an immutable reference of a captured value. Now the captured value in this closure here would be x, right? This vector, because the closure captures it from the environment it is defined in. And this should actually work. Let's see. As you can see, when we pass this closure to this function, and we define here that the closure must implement the fn trait, taking a usize as argument and returning a bool, then we are calling the closure, right? Func here holds a closure, so we are calling it with 3. In this case, this would evaluate to true, because the length of vec is 3 elements, right? So x.len will return 3, meaning it's equal to the provided argument. And 4, of course, would return false. So we are here initializing a string, and over here we are defining a closure. It takes an argument and it then modifies this string over here, basically pushing the string that was provided in the argument. Then we are calling the exec function, providing it this closure. All right. Then let's see. All this function does, it takes a closure as an argument, and then it will call the closure, and it will pass it a string literal, right? Meaning that to this string s, this string literal will be pushed, right? So after calling this closure, s should then hold hello. All right. And then we just print out s. Now, what would be the appropriate trait bound for this closure? Think about it. We have fn, fn mute, and fn once. So what would be the least restrictive approach? It would be fn mute, right? Because we are mutating here this string, the captured value, but we don't need to take ownership in order to be able to mutate it, right? Now we have to provide the argument. This would be of type string slice, right? We are passing here the string literal, which is string slice. And then we have to provide a return type. So actually, this won't return anything, right? So we don't here have to provide a return type. So let's see if this works. And as you can see, we have here a lifetime parameter. And this is just ensuring that the passed string literal here is actually outliving this function exec, right? Which is the case because string literals, remember, are static lifetime. They live the entire duration of the program. And as you can see, when we print out s, it has successfully been modified. So it's sufficient to use here fn mute, but if we want, we can even take ownership. But then we have the restriction that we can only call this closure one time, right? So if we try that, As you can see, this is working too. Which trait does the compiler prefer to use? fn, the closure uses the captured value by reference. fn mute, the closure uses the captured value by mutable reference. fn once, the closure uses the captured value by value. On a variable by variable basis, the compiler will capture variables in the least restrictive manner possible. For instance, consider a parameter annotated as fn once. This specifies that the closure may capture t by reference, by mutable reference, or taking ownership. But the compiler will ultimately choose based on how the captured variables are used in the closure. Which trait to use is determined by what the closure does with captured value. This is because if a move is possible, then any of borrow should also be possible. Note that the reverse is not true. If the parameter is annotated as fn, then capturing variables by mutable reference or by t is not allowed. Let's see number 7. Fill in the blank. A function which takes a closure as an argument and calls it. F denotes that f is a generic type parameter. So as you can see, we have here the function apply, and it takes as an argument a closure, and all it does, it will then call this closure, right? And we have here to define the trait bound for the provided closure. A function which takes a closure and returns an I32. So over here we have apply to 3, again taking a closure, and we have then to define here the trait bound. The closure takes an I32 and returns an I32. And again, this function over here will just call the closure, and the difference is it will then return the returned value from the closure. So as you can see over here, it just calls the closure, but it doesn't return anything because here this is a statement. It's ending with semicolon. Here we omit the semicolon, meaning the return value of the closure will be the return value the function returns. All right. So over here we have a string literal, a non-copy type. ToOwned creates owned data from borrowed one. So as you can see, we take a string literal and call the ToOwned method. Now the ToOwned method will convert a string slice to a string. Capture two variables, greeting by reference and farewell by value. So over here we have a closure. Then greeting is by reference requires fn. So as you can see, this closure captures the greeting variable. Now all it does, it will print it out, meaning to take an immutable reference would be sufficient. So the compiler will implement the fn trait for this closure because it is sufficient to only take an immutable reference to the captured variable. All right. Mutation forces farewell to be captured by mutable reference. Now requires fn mute. So as you can see, we are taking farewell and we are modifying it. Now this requires farewell over here to be captured as a mutable reference. Again, you can see that the compiler tries always to use the least restrictive approach. So then the compiler will instead implement the fn mute trait for this closure. All right? Because again, we capture here a variable which needs to be mutated. Then manually calling drop forces farewell to be captured by value. Now requires fn once. So this mem drop here allows that we manually drop a value from memory, right? But this actually requires that we take farvel as a value, right? So the closure should take ownership of this variable, meaning the compiler will now implement the fn1 trait for this closure, right? So as you can see, step by step, here an immutable reference was sufficient, so it just implements the fn trait. Here a string got mutated, so it takes the captured values as immutable reference, meaning fn mute is implemented. And here, when a function needs to take ownership, then of course the captured value must be captured as owned type, meaning fn1 is implemented. So that means if this closure implements the fn1 trait, it can only be called once, because you have inside values that capture the environment values by taking ownership. Call the function which applies the closure. So we call the apply function here, providing it an argument diary. This closure here, right? We are calling apply and providing diary. Now let's see. This would be this function. And as we've seen, because farvel here gets captured by value, meaning the closure takes ownership, we have to define here that it will be a closure that implements the fn1 trait, right? Now, as you can see, the closure doesn't take any argument and it doesn't return anything. So we would annotate it like that. So again, this just defines that the generic type f must implement the fn1 trait. And over here, double satisfies apply to tree trait bound. So here we have a closure taking one argument and it returns the result of this operation, right? So we call the apply to tree function, providing it as argument this closure. And as you can see over here, apply to tree is a closure, generic type f, and we here define that the type f must implement the fn trait. And as you can see, it takes as an argument an i32 and the return value and the return type will be i32. So let's see, I take this closure here and this closure was passed as an argument to this function. And all this function does is it will call the closure with an argument of 3. Now x here will be replaced by 3 and the return will be 2 times 3, which would be 6, right? So this closure then returns an i32, namely 6. And as you can see, because we omit here the semicolon, it means that the return value of this closure will be the return value of this function. So when we call this function over here, the return value over here will be 6. And as you can see, this is all compiling. Move closures may still implement fn or fn mute, even though they capture variables by move. This is because the traits implemented by closure type are determined by what the closure does with the captured value, not how it captures them. The move keyword only specifies the latter. So the move keyword only specifies how the captured values are captured, while the fn traits determine what the closure does with the captured values. So as you can see, we have here a string and we have here a closure with the move keyword, meaning values will get moved inside this closure. Now, because over here, as you can see, s in this case doesn't need to be taken as value. So the closure doesn't need to take ownership of the data because it will just print it out, right? So an immutable reference would be sufficient. And that's exactly what this says. So over here, as you can see, we are calling the exec function with this closure. And when we see over here, the exec function takes as an argument a closure that implements the fn1's trait, all right? So it will in fact take ownership of the captured value. And then in the function itself, it will just call the closure and returns the return type of the closure. Now over here, as you can see, again, we have a string and we have a closure. Even though we have the move keyword, as you can see, we define here that the provided closure to exec only has to implement the fn trait. So the string s here will get moved. So basically this closure here takes ownership, but we can still define this closure over here to just implement fn. Because again, even though we are taking ownership, we are just printing out, right? The difference between move and the fn traits is the fn traits define what the closure does with the captured values, and move defines how it captures them. So it would capture here by taking ownership, but the fn trait only defines what are we doing with the captured value. In this case, we are just printing it out, meaning an immutable reference would be sufficient. So we can even here pass fn and it still would work. Fill in the blank. So over here we have a string, and this would be a closure that takes an argument and returns a string. Now, what we do over here is pushing to this string the provided argument, right? And then what we do is we will return s, meaning this string, right? So when we call over here this function and provide it the closure, then we have to implement the fn1 trait. And it will take as an argument a string literal. Let's annotate that with the lifetime parameter a, and it will return a string, right? So this would be the trait bound we are defining here. Now, why did I implement here fn1s, or why did I define that f over here, the type of the argument, must implement the fn1s trait? Because as you can see, we are capturing s and modify it. Now over here, it would be sufficient to use an fn mute, right? Now, again, it would be sufficient to just use a mutable reference to s. But again, we are here returning s, right? We are returning this captured variable, meaning we must be the owner to return something. So we have to define that f should implement the fn1's trait, right? Because we are here returning s, meaning the closure must be the owner in order to return it. Let's see. And this is compiling. Input functions. Since closure can be used as arguments, you might wonder, can we use functions as arguments too? And indeed we can. So as you can see, we have here the call me function. Implement call me to make it work. And over here we have a normal function just printing out something, and in main here we have a closure, right? Also just printing out something. Then we call the call me function here 2 times, 1 time with a closure and 1 time with a function. And that means, let's see, first of all, we define, we want here a type f, which is generic. Okay, so we have to define here a generic type parameter. And then of course we have to define a trait bound, right? So in this case over here, we are not mutating anything and we don't need to take ownership. And in fact, over here, we don't even capture any variables, right? It will just print out something and it doesn't capture anything. So in this case, the fn trait is sufficient, right? And by the way, they don't take any argument and they don't return anything. So let's see. And this will be the output. So we call me, providing it the closure implements the fn trait, and then call me will just call the provided function and closure, right? Meaning when they are called, they will just print out this over here. Of course, closure first, because closure has been called first. Let's see exercise 10, closure as return types. Returning a closure is much harder than you may have thought of. Now it's actually not that hard, but you will see. Fill in the blank using 2 approaches and fix the error. So as you can see, we have here the create fn function, and we have to define here the return type. So let's first see. We have over here a variable that is declared inside the function, meaning num will only live as long as this function lives, right? And then over here, we are returning a closure. Notice we omit here semicolon, meaning this whole closure will actually be returned by the function. And when we go into main, as you can see, we call the create fn function. Then this function should return a closure, meaning fn plane will hold a closure. Basically, fn plane will look something like that, right? Holding a closure, meaning we then can call the fn plane closure with a integer, all right? Because we have to define here that x should be of type i32, because we here capture num, which is of type i32. Remember, when we perform an operation, both values must be of the same type. Now, let's see. We call the create fn function. Then we initialize the num variable, and then we have here the closure that will get returned, meaning num here will capture this variable. And when we then call the closure over here that will get returned by create fn, then we provided a value of 1, meaning x will be 1 and num will be 5, right? Meaning the value, the output should be 6 then. when calling, let's write it here, after calling the closure itself, the output should be 6. Now let's see. First of all, we have to think about how is this num variable captured. Now again, the compiler will use the least restrictive approach, so it will just take a reference. The problem here is that we actually return this closure, right? So num actually must outlive this function. Otherwise, when we return the closure and num gets out of scope, then over here we hold a closure that refers to something that got out of scope. So let's use the move keyword here, meaning num gets moved into the closure. So the closure will become the owner of this variable. All right. Now, again, here we can use static dispatch or dynamic dispatch. Now, I will go first with static dispatch. So in this case, we want to return a type that implements the fn trait, right? Because over here we have the closure that we want to return. So let's implement that. This closure should implement the fn trait. And again, over here, fn is sufficient because even though we have captured the num by ownership, the actual closure only performs an operation. So it doesn't modify num. And remember, move defines how we capture the closure, and the fn traits define what the closure will do with the captured value. All right, so fn here is sufficient, and this closure takes as an argument an i32, right? Because the argument and the num variable must match because we are performing an operation on them. And the return type should also be i32, all right? The result of this operation. So let's see. And this is compiling. Now let's actually see the output. As you can see, the output will be 6. Now this is using static dispatch. Now we can also use dynamic dispatch. Remember, when dealing with trait bounds like this, we then have to basically box this over here, and we put this over here into a box, right? This would then be a trait object. We are using dynamic dispatch here. So let's see. And this is also working. So we have implemented the return type in 2 approaches. Fill in the blank and fix the error. So as you can see, we have the function factory taking one argument of type i32. Over here we have a variable of type i32, and if x, the provided argument, is bigger than 1, then this will be returned, and else, if it is smaller than 1, this closure will be returned. So using here the static dispatch approach doesn't work, okay? We cannot do something like that, because over here we don't know exactly which closure gets returned. And as you've noticed, they are identical, right? But in fact, this closure is different than this, because these have been both declared and they are located in different memory locations. All right. So even though they are exactly the same, the compiler can't know at compile time which of these closures will get returned, because they live at different memory locations. Now, what we can do over here is using the dynamic dispatch approach. So for that, again, we are boxing these closures and we define here that the return type will be a box that holds a trait object, namely a trait object that implements the fn trait, taking as argument an i32, this x here, and returning an i32. Right, let's see. Right, and we have to provide here the main function, because otherwise the program won't compile. And this is compiling. All right, see you in the next topic. So iterators will be the last topic we will cover together. So let's dive in. An iterator allows to perform a task on a sequence of items in turn. Iterators are lazy, meaning they have no effect until methods are called that consume the iterator to use it up. All iterators implement the iterator trait, which provides the next method, which gets called automatically when traversing over some data. And some methods consume the iterator, while others produce a new iterator from the provided iterator. Let's see. The iterator pattern allows us to perform some task on a sequence of items in turn. An iterator is responsible for the logic of iterating over each item and determining when the sequence has finished. So over here we have a vector, and then we are iterating over the elements in this vector. And as you can see, the variable x will hold in each iteration one element of the vector. So when we print that out, as you can see, in each iteration it will just print out x, which means x in the first iteration is 1, then 2, and then 3. In the code above, you may consider for as a simple loop, but actually it is iterating over an iterator. By default, the for loop will apply the into iter to the collection and change it into an iterator. As a result, the following code is equivalent to the previous one. So this is happening implicitly, that v over here, this vector, or really any collection, will be called with this into iter method, meaning this collection will be converted to an iterator, right? And then we traverse over each item. So let's see exercise 1, refactoring the following code using iterators. So we have here an array holding 10 elements, which are all 0. Something like that, okay? 10 times. Then we have here a for loop iterating from 0 to array length, where the actual length is excluded, meaning from 0 to 9, right? 10 times. And then we just index into this array and print out the element living at the specific index. So when we execute that, as you can see, we print out 10 times 0. Now again, we don't have to use this syntax. We can just pass here the array itself and it will do exactly the same. And we have seen that the compiler implicitly will put that into an iterator, like that. And as you can see, this would be the exactly same thing. One of the easiest ways to create an iterator is to use the range notation. So over here we are initializing an empty vector, right? Then we want to iterate here over a range. And in each iteration we are just pushing n to the vector. Now in the end, the length of this vector should contain 100 elements, right? So what we can do over here is going from 0 to 100, meaning 100 is excluded, going from 0 to 99, meaning the vector will then hold elements from 0 to 99. Like that, right? 100 elements. And this will compile. Next method, all iterators implement a trait named iterator that is defined in the standard library. As you can see, this is the iterator trait that is defined in the standard library. It has an associated type item, which basically refers to the type we are iterating over. For example, a vector of u8, then the item type will be u8, right? And as you can see, each type that implements the iterator trait will implement the next method, taking a mutable reference to the instance and returning an option containing the type of the associated type defined here. And we can call the next method on iterators directly. So over here we have a vector, and we can then put that into an iterator, right? So this will then actually hold an iterator, right? And not a vector anymore. So we put this collection into an iterator, meaning we then can use the next method that is implemented for the iterator type. And that is actually exactly what is happening when you are doing a for loop, for example. In the back, the Rust compiler will just call next all the time until it reaches a point where there is a non-return, because remember, this next method will return an option type. So when we put that into an iterator and call next, we will get a sum and the first element, right? Then sum and 2, and as you can see, we don't have any more elements, so it will return none, right? This is the option type, and we have covered that. And when we put a collection into an iterator, it should be mutable, right? So the next method takes a mutable reference we have seen, so we have to make it mutable. All right? Into iter, iter, and iter mute. In the previous section, we have mentioned that for will apply the into iter to the collection and change it into a iterator. However, this is not the only way to convert collections into iterators. Into iter, iter, and iter mute, all of them can convert a collection into an iterator, but in different ways. So into iter consumes the collection. Once the collection has been consumed, it is no longer available for reuse because its ownership has been moved within the loop. Iter, this borrows each element of the collection through each iteration, thus leaving the collection untouched and available for reuse after the loop. And itermute, this mutably borrows each element of the collection, allowing for the collection to be modified in place. So as you can see, we have here a vector. And then we loop over this vector here, right? And all we do here is actually printing out each of the elements. Now we have seen that implicitly the compiler will call here into iter, meaning the iterator will become the owner of this data, right? So we can't reuse this R after we have put it into this iterator. But there is not a solution. We can just use iter here because it's sufficient that we have a mutable, because it's sufficient here that we have an immutable reference, right? We just want to print it out. We don't need to mutate anything or anything else. We only need read-only data, right? So let's see. And as you can see, we then iterate over each element, printing it, this over here, and then we can reuse the collection over here. So ownership hasn't been transferred into this iterator. 5, fill in the blank. So over here we have a vector with string literals, okay? And then over here we are iterating over the elements in this vector. Now, as you can see, we are here matching the element, and if it is a mutable reference to the string literal varies, then we will actually modify the element that we are iterating at this exact moment to this over here. If it is anything else, then it will be replaced by hello, right? So in the first iteration, name will hold a string literal, this over here. Then we match this, and in this case, this arm will match, meaning we assign string literal hello to this element, right? So instead of Bob, we would then have hello in the first index, right? So as you can see, we are mutating, meaning we can here use iter mute, right? We want to take mutable references from this vector. But as you can see over here, we are again using this names vector, meaning we can't take ownership. So let's see. And this is compiling, and as you can see, the first two elements got replaced by hello, and the last one, Ferries, has been matched here, right? Name holds a mutable reference to the string slice Ferries. And that's why this will get returned, meaning it will be assigned to this element. Let's see exercise 6, fill in the blank. As you can see, we have here a vector. Now over here, we want to put this vector into an iterator, right? Now, before we do that, as you can see, this is the vector in the beginning, and this is how it should look like in the end. So we want to mutate the first element. So in this case, we take it as mutable references, calling the itermute method, right? So we take from here mutable references of the elements in this vector. Then over here we can call the next method, which will then give us back an option type of the first element, right? So we pattern match here sum with the inner value. And then what we can do, because we get here a mutable reference, meaning we can dereference it and assign it a new value, like that. So we get no output. Let's actually see the elements. As you can see, we changed the first element. We have mutated it using iter mute, right? Getting back a mutable reference to the elements. Creating our own iterator. We can not only create iterators from collections type, but also can create iterators by implementing the iterator trait on our own types. So as you can see, we have here a custom type counter, which has one field. And we implement here the associated function new, basically just creating an instance. And then over here, we implement the iterator trait for counter, right? So first of all, we have to give the associated type a concrete type, in this case U32, right? Basically the type this field is holding. Then we implement the next method. As you can see, next takes a mutable reference to the instance, and it returns an option that holds a type of the associated item here, right? It would be U32 in this case. So if self.count is less than 5, then we increment the count field here and we return the actual count. Otherwise, we return none. So if self.count is bigger than 5, then it returns none. So as you can see, we are then creating a new instance of this counter type using the new associated function. And then, as you can see, when we call the next method on it, right, because we can do that because we have implemented the iterator trait for our custom type. So when we do that, we just get back the value of count. As you can see, when calling next, then over here it checks, is the self.count field less than 5? In this case it is, right? We didn't increment it so far, so it should hold 0. And in that case, it will increment it by 1, right? The count field over here gets incremented by 1, and then it returns it, and of course packing it into a sum, because we return here an option type. So that means we get 1. In the next iteration we will get 2, 3, 4, 5, and then as you can see, the count field holds a value of 5, meaning this won't get, meaning this would evaluate to false and this will get executed, right? So we will get back a none. And over here we have Fibonacci. So the Fibonacci sequence starts at 0, then 1, then 0 plus 1 is 1, then 1 plus 1 is 2, then 1 plus 2 is 3, 2 plus 3 is 5, 5 plus 3 is 8, and so on, right? And as you can see, we have here the struct Fibonacci that has a current field and a next field. So as you can see, current, for example, would hold 0 and next would hold 1. And as you can see, we are implementing the iterator for Fibonacci. So we define here the return type to be U32, right? Or basically the type of the items we are iterating over. So both of these fields hold U32. And over here we have a function Fibonacci, which just returns an instance of the Fibonacci struct with current holding 0 and next holding 1. So notice something here. When we call next, we actually want to return some 1 and not some 0. So this is important, but let's now implement the next method. So we have seen that it will return an option type holding self item, right? The type that is defined in the associated type item. And then over here, I will create a new variable forward, and this would then be self.current plus self.next, right? Because so forward in this example would be 0 plus 1, right? This would equal 1. So we can then, to go one step forward, we want to go like this and then like this, right? We can assign to self current self next, meaning in the next iteration the current field will hold 1, right? And self.next will hold forward, right? Self.current plus self.next, meaning in the next iteration next will hold 1. So we will be at this point, right? And then all we need to do is we wrap it in sum, because again we return an option and we return the current field over here. Let's see. Methods that consume the iterator. The iterator trait has a number of methods with default implementations provided by the standard library. Consuming adapters. Some of these methods call the method next to use up the iterator, so they are called consuming adapters. So over here we have a vector and we put that into an iter. Notice we take here the iter method, meaning it will just take immutable references to the elements. And then we call on this iterator the sum method. The sum method will take the ownership of the iterator and iterates through the items by repeatedly calling next method, right? So all this sum method does, it will just add together all the elements in the vector. And notice sum will take ownership of this iterator, meaning we can't use v1 iter again, right? So in this case the total will be 6. Now I can't edit here. Let's do it in the playground. So we have here a vector and then we put it into an iterator and then we call the sum method on the iterator. Meaning this should then hold I32 and the value should be 6, right? Just adding all of these together. Now that means we can't use v1 iter again here. This is not possible because the sum method will take ownership of the v1 iter variable. Let's see. As you can see, this is compiling. Let's actually print out the result. As you can see, we would have 6. Collect. Other than converting a collection into an iterator, we can also collect the result values into a collection. Collect will consume the iterator. So over here we have an array which holds 2 tuples, right? And each tuple has as And each tuple has a string literal and an I32, right? Then we take this names array here, put it into an iterator, notice here into iter, meaning we take ownership of these elements. And then we collect, meaning we collect it into another collection which has to be annotated here. Meaning we will then create a hash map with string literals as keys and I32 values, right? Then we print it out here, and over here we have a vector of I32 types, and we call the iter method over here, meaning we just take references to this vector. And then over here we call collect, meaning it will get collected into an iterator, right? Because we want here v2, meaning, and then we annotate here that we want a vector of I32 because, as you can see, v2 should hold a vector with these elements. Let's see. And actually over here we would have references of I32s, right? Because again, iter here takes references of these elements, meaning they would not equate. We want a vector of I32 elements, meaning we can call the into iter, and that means ownership of these elements will be transferred to v2. And this would be the output of the print line over here. We are printing here out the hash map we have converted. Iterator adapters. Methods allowing you to change one iterator into another iterator are known as iterator adapters. You can chain multiple iterator adapters to perform complex actions in a readable way. But because all iterators are lazy, you have to call one of the consuming adapters to get results from calls to iterator adapters. So over here, fill in the blanks, we have a vector and we iterate over the elements, just taking immutable references. All right. Then over here, you can see we want to modify the elements inside this vector to look something like that, basically just incrementing each element. Now we can use here map to do that, right? Now map will create another iterator. It will take ownership of this iterator here, and it will then create another iterator, right? But with the modified elements. And then we can call here collect to actually put it into a collection, meaning this vector over here. Let's see. All right, this is compiling. I guess this would be I32 because we have taken it from this vector. So this is compiling. Let's actually output. As you can see, we have modified the elements. But of course, v1 is still accessible, and that is because we have called here the iter method, meaning we just take immutable references of the elements in this vector, meaning the ownership will remain at v1. So we have now reached the end of this course, and if you have made it this far, then your dedication to this language is really impressive, and this is only the beginning of your journey. I hope this course was helpful. Don't forget to spread the word about free software, and I'm out.